let's talk about the fabrication of advanced nuclear fuels. Fuel fabrication is the last step in the process of turning uranium into nuclear fuel rods. Batched into assemblies, the fuel rods form the majority of a reactor core structure. This transformation from a fungible material, uranium, to high tech reactor components is conceptually different from the refining and preparation of fossil fuels. Utilities and fabricators have collaborated to greatly improve fuel assembly performance, and an international accident tolerant fuel program is underway. Basically, fabrication of advanced nuclear fuels involves the production of fuel assemblies or elements that are used in nuclear reactors. And advanced nuclear fuels are designed to improve the performance, safety, and efficiency of nuclear power plants compared to traditional fuels. Let's talk about the powder preparation. Basically, fabrication of advanced fuels are done by two process, which is powder preparation and powder process. Let's talk about the powder preparation, chemical synthesis, and mechanical alloying. Uh, let's discuss about the chemical synthesis. It is the first step. Uh, is often the synthesis of the fuel material in powder form. This can involve various chemical processes such as uh, pres- precipitation, sol gel synthesis, or chemical reactions to produce the desired fuel compound. Mechanical alloying. In some cases, mechanical alloying is employed to produce a homogeneous mixture of different fuel materials. This process involves grinding and blending the powders together using high energy ball mills or similar equipment. Second point is powder processing, blending and mixing, consolidation, sintering. Blending and mixing. If multiple powders are used, they are thoroughly mixed to achieve a homogeneous blend. This step ensures uniformity in the composition and properties of the fuel. Consolidation. The blended powders may undergo consolidation processes to form a solid fuel material. Common consolidation techniques include cold pressing, hot pressing, or spark plasma sintering. These methods apply heat and pressure to the powder to promote densification and bonding between particles. Sintering is a heat treatment process that further enhances the densification and strengthens the fuel material, and the consolidated fuel is heated to a specific temperature below its melting point to promote atomic diffusion and solid state bonding. Let's talk about the pelletization and sintering. It is the most important step in the fabrication of various materials, including advanced nuclear fuels. Let's look at each process in more detail. Pelletization involves shaped powder material into small, dense pellets. In the context of nuclear fuel fabrication, it is typically performed after the powder preparation and blending steps. The process helps in improve the fuel's mechanical strength, facilitate handling, and control its geometry for efficient use in nuclear reactors. The pelletization process generally involves the following steps. Here are some steps that are generally involves for example, powder loading, compaction, ejection, trimming, and surface preparation. Let's talk about this second point, which is sintering. Sintering is a heat treatment process that follows pelletization and further enhances the densification and bonding on the fuel pellets. The primary objectives of sintering are to improve the pellets' mechanical strength, enhance its stability, and promote diffusion and bonding between the fuel particles. The sintering process typically involves the following steps, which is heating, densification, or bonding, cooling. So let's talk about its treatment and conditioning. Post fabrication treatments and conditioning steps are carried out on nuclear fuel pellets after pelletization and sintering to optimize their properties, ensure compatibility with the reactor operation, and meet safety requirements. Here are some common post fabrication treatments and conditioning process. Hot isostatic pressing. Hot isostatic pressing is a post fabrication treatment that subjects that fuel pellets to high temperature and pressure in an inert gas environment. This process helps to eliminate residual porosity, uh, improve pellet density, and enhance fuel performance and mechanical strength. And the second point is oxidation and reduction treatments. Depending on the fuel composition and specific requirements, oxidation or reduction treatments may be employed. These processes involve exposing the fuel pellets to controlled atmospheres or chemical reactions to adjust the fuel's chemical composition. Such treatments can influence the fuel's behavior in terms of reactivity, stability, compatibility with the reactor environment. And the third point is inspection and quality control. After post fabrication treatments, the fuel pellets undergo through inspection and quality control procedures. This includes visual examination, dimensional measurements, non destructive testing methods. For example, ultrasonic testing and other analysis techniques to verify the quality, integrity, and compliance of the fuel pellets with specified standards. So let's talk about the characterization of advanced nuclear fuels. Characterization of advanced nuclear fuels involves a range of techniques and analyses to assess their properties, behavior, and performance. The characterization methods used can vary depending on the specific fuel type, but here are some common techniques employed, uh, which is microstructural analysis, X-ray diffraction, fuel performance testing. Let's first discuss about microstructural analysis. Let's talk about microstructure analysis, which involves the examination of the fuel material at a microscopic level to study its grain structure, porosity, and the distribution of phases or constituents. Techniques such as optical microscopy, scanning electron microscopy, and transmission electron microscopy are used to visualize and analyze the microstructure. X-ray diffraction is used to identify the crystal structure and phase composition of the fuel material. It provides information on the arrangement of atoms within the crystal lattice and can detect any structural change, such as phase transformations or the presence of impurities. And the third point is fuel performance testing, which is used in pile irradiation experiments, is a crucial aspect of evaluating the behavior and performance of advanced nuclear fuels under realistic reactor conditions. In pile irradiations experiments involve subjecting fuel samples to neutron irradiation inside a nuclear reactor, allowing researchers to study various fuels parameters.